Hello, good day. My name is Olushola Timothy Ogundepo. Today, I'll be taking you through the statistical machine learning assignment that I just concluded. I work on the DNA microarray dataset, which is on the prostate cancer. So this particular dataset is actually an ultra high dimensional dataset. Clearly, the data shape and dimensionality of dataset still tell us the same thing. The number of samples that we have in the dataset is 79, whereas the number of features is 500. If you look at it, you see that the kappa is 0.158. This is telling us that this dataset is containing ultra high dimensionality. All the data type in this particular dataset are actually continuous. This is telling us that most of all the gene dataset, mostly, they are actually normalized. But before we go further, let's look at the response variable distribution. As you can clearly see here that those that have cancer in this dataset and those that don't have cancer in the dataset are actually balanced, which is telling us that 37 non-cancer samples in our dataset is just 46.8, while the 42 cancer sample is just 53.2%. This sample is fairly balanced. Moving to the Kruskal-Wallis test for most powerful predictors in our dataset. This particular Kruskal-Wallis test is used for non-parametric tests, which is to test the difference in medians across groups of our dataset to be able to see the features that has discriminative power between cancer and non-cancer. The Kruskal-Wallis test with higher value is actually showing us that this particular variable has a strong discriminative power to tell the difference between cancer and non-cancer. And here we have the top 9 predictors variable, which have strong predictive power for cancer and non-cancer. Plotting this shows all the features that actually have strong discriminative power for the cancer and non-cancer dataset. To show how they actually discriminate between cancer and non-cancer, here are the top most powerful predictors. As you can see, we can clearly see that this particular features is actually able to separate both cancer and non-cancer. Without wasting our time, let me quickly go to the tree structure analysis. When I use the CP to be 0.01, we can clearly see that in the tree structure that we only have 4 terminal leaf nodes, and the mathematical representation of these 4 terminal leaf nodes are stated here. In our case, the root leaf node is this particular variable. This is the one that has the strongest initial separation between cancer and non-cancer in the dataset. Clearly, there is no way we have strong predictive power in all the features without having the weakest predictive power among all the variables. The one for cancer and the one for non-cancer, they can't really separate them that much. Looking at the box plot, this is telling us that same thing. Looking at the correlation between all the features in this dataset, we can clearly see that there is high multicollinearity in the dataset. The positive one are the one that are blue, while the negative correlation are the one that are red. And we can clearly see that in this particular correlation plot. In this section, I trained 6 different models. Take for example, for the k-nearest neighbor, we have 1 k-nearest neighbor, 7 and 9. For the tree model, we have CP to be 0, which is telling us that this is a fully grown tree, and also CP to be 0.05 and 0.1, which is a regularized tree. In this particular ROC, I trained the model using the entire data set and also test the model using the entire data set. And clearly we can see that this model with one neighbor actually overfits because it's able to predict everything well. And looking at the other ones, they also perform quite good, which is telling you that this is not actually trustworthy, because training a model and also testing it on that same model cannot really tell us much about the performance of that model, because we are not using unseen data. From theoretical standpoint, having the training error to be minimized for the k nearest neighbor when we specify k to be 1 is actually expected, because it has actually overfit, it has learned the noises. And also for when we specified CP to be equals to 0 for the tree, that one too performed well. So it's expected because they actually learn noises along the way. We testing it using that same data set again, they will perform well. Basically, the place to know whether the model perform good or not is when we have stochastic holdout with, take for example, 100 replication. In our own case here, I have 70% training and 30% testing. We replicated it 100 times, and this particular box plot actually confirmed that. We can see that when we have 9 neighbors, the errors is actually minimized compared to when we have 1 neighbor and 7 neighbors. And these other trees actually perform somehow bad for this our data set. So in this case, I will actually go for 9 neighbors, because this one actually helps us to minimize the error on the testing set. This one is actually trustworthy. because this is an unseen data and it has not seen it before, compared to when we have one neighbor which has already seen everything and we are still testing it on that same data set again. That's overfitting basically. Checking the ANOVA statistics on our models, we can clearly see that when we have the p-value to be 0.00123, this is telling us that the model provides a strong statistical evidence that the mean test error are not equal across all the 6 different models. One of the key criteria of what I learned is that never to trust the training error, because take for example, the 3 model perform well on the training model, but now when we now give it the test data set, basically it perform poorly compared to those that actually perform somehow poorly on the training error, but now they were able to generalize well to the testing data set. Thank you for your time. Bye.